The Selfish Gene by Richard Dawkins. Picture a tiny warrior on what can only be described as a suicide mission. No hesitation, no second thoughts. The moment it strikes in defense of its home, it signs its own death warrant. This isn't some dramatic war movie. It's happening right now in your backyard. We're talking about the humble honeybee. When it plunges its stinger into a threat to the hive, that stinger rips away from its body, and within hours, the bee is dead. But here's the puzzle that should keep you up at night. Why on earth would evolution create a creature programmed for self-destruction? What possible advantage could there be in building an animal that kills itself to protect others? Are bees just really into teamwork? The real answer is going to blow your mind. It's one of those ideas that, once you hear it, makes you see everything differently. Like finding out you've been reading a map upside down your whole life. This revelation came to the world in 1976, packaged in a book that sold over 1 million copies and sparked more dinner-table arguments than any biology text has a right to. The book is called The Selfish Gene, and its author, Richard Dawkins, a young researcher at Oxford at the time, had the audacity to suggest something radical. We're all just machines. Sophisticated robots, sure, but robots nonetheless, built to serve our true masters, our genes. Today we're diving deep into this mind-bending idea. Dawkins describes nature as a place of ruthless competition and cunning deception, which sounds pretty grim. But here's the twist. This same framework explains the most beautiful moments in nature. That sacrificial bee, a parent sacrificing everything for their young. Acts of kindness that seem to defy logic. Here's what I'm offering you. By the time we're done, you'll understand the fundamental principle driving all life on this planet. You'll see yourself not as a single, unified individual, but as a temporary alliance of ancient genes, each playing its own survival game. It's unsettling, sure, but it's also thrilling. And the best part? Once you understand the game, you can choose whether to play by the rules. Unlike every other creature on Earth, we can see the strings and decide whether to dance. Let's rewind to the ultimate beginning. Not your beginning or even humanity's beginning, but the start of life itself. The question driving this entire book is beautifully simple. Why does life exist at all? For billions of years, living things existed without a clue why they were here. Then Charles Darwin showed up with his revolutionary insight. Evolution by natural selection. Life wasn't designed. It started simple and stumbled its way toward complexity over unimaginable spans of time. Dawkins takes Darwin's brilliant framework and cranks it up to 11. He argues that we've been focusing on the wrong players. We watch animals, packs, species. But the real protagonists in this story are far tinier and far older. The gene is the star of the show. Genes are the replicators, the truly immortal entities. And everything else, including you and me, is just temporary equipment in their survival game. To grasp this, we need to travel back roughly 4 billion years to what scientists charmingly call the primeval soup. Picture the early oceans, not the pristine blue waters of a vacation brochure, but a murky, warm chemical stew of methane, ammonia, and water. Lightning crackles overhead, the sun beats down, and all that energy is causing these simple chemicals to combine into more complex molecules. For millions of years, this is just random chemical chaos. But then something extraordinary happens. Through sheer accident, a molecule forms that has one magical property. It can copy itself. Dawkins calls this the replicator. Think of it as a molecular template. The smaller molecules floating around in the soup naturally stick to it, and when they do, They arrange themselves into a perfect copy of the original. Suddenly, the oceans start filling with copies of this remarkable molecule. But copying is never perfect. Mistakes happen. These errors create variations, and now we have competition. Which variety of replicator will dominate? The answer comes down to 3 traits. Longevity. The longer a molecule lasts, the more copies it can make. Fecundity. The faster it reproduces, the more abundant it becomes. And copying fidelity. The more accurately it reproduces, the better its successful design persists. This is evolution in its rawest form. No intelligence required, just the blind law of survival of the stable. The most successful replicators start taking over the soup. As raw materials become scarce, the competition intensifies. These replicators develop tricks. Some learn to break apart competing molecules and steal their building blocks. The first primitive predators. Others build protective protein walls around themselves for defense. And just like that, we have the first living cells. The replicators had constructed the very first survival machines. Jump forward a few billion years. Where are those ancient replicators now? They didn't vanish. They're masters of survival. They're inside you right now. We call them genes, and we, you, me, every bird and fish, are their survival machines. This is the heart of the book. We're all temporary vehicles, elaborate machines our genes have built to protect themselves and make more copies. A monkey is a machine for preserving genes in trees. A fish is a machine for preserving genes in water. When we've served our purpose, our bodies are discarded. But the genes themselves? They're potentially immortal, passed down through countless generations. So how does this actually work? Your genes are made of DNA, tucked inside your cells. Think of your DNA as an architect's blueprint for building a body, written in a 4-letter code. In humans, these blueprints fill 46 volumes, our chromosomes. And here's the wild part. Every single cell in your body contains a complete copy of all 46 volumes. It's like having the full blueprints for an entire city hidden inside every brick. Genes control the construction by supervising protein production. Proteins aren't just building materials. They're the master chemists running all the processes in your cells. But genes don't micromanage. They're more like programmers. They write the software for building a body and brain. Then the survival machine is set loose. Why this hands-off approach? Time lags. Building a body takes months. But behavior, dodging a predator, catching prey, happens in split seconds. Genes can't react that fast. So they do the next best thing. Build a fast onboard computer, a brain, and program it with general survival strategies. It's like programming a chess computer. You can't specify every move for every possible game. There are more possible chess games than atoms in the galaxy. Instead, you give it principles. Protect your king. Control the center. Genes do the same. Pain is bad. Avoid it. Sweet things are good. Eat them. This pre-programming gets refined through learning. But the world is unpredictable. Genes make predictions based on past success. Polar bear genes predict a cold environment, so they build in thick white fur. These aren't conscious predictions. It's just that bears with genes for thick fur survived better in the past. One of our brain's most remarkable abilities is simulation. Before making a decision, you can imagine different outcomes in your head. You run a mental model of the world. This is faster and safer than trial and error, because imaginary mistakes don't kill you. Dawkins suggests that consciousness itself might have emerged when the brain's simulation of the world became so complete it had to include a model of itself. Here's where it gets really interesting. The brain, the executive machine, starts making more and more decisions independently from the genes. It can even rebel, like choosing to use contraception, deliberately not having children, despite being perfectly capable. We alone can rebel against the tyranny of our selfish creators. But before we rebel, we need to understand the rules of the game our genes have built. That world is defined by conflict and cooperation. Let's start with aggression. Why do animals fight? You might think that survival of the fittest means killing every rival. But in nature, fights often look more like formal duels, with rules and surrender signals. Why the restraint? The answer came from mathematician John Maynard Smith, who applied game theory to animal behavior. He developed the concept of the evolutionarily stable strategy, or ESS. An ESS is a strategy that, once most of the population adopts it, can't be beaten by any alternative. Imagine a simple game with two strategies, hawk and dove. Hawks fight viciously until someone gets seriously hurt. Doves just posture and threaten, but never actually harm anyone. When a hawk meets a dove, the dove retreats immediately, so the hawk wins easily. You'd think hawks would take over. But what happens when hawk meets hawk? They fight until one is badly injured or dead. In a population full of hawks, everyone's constantly getting mauled, so the average payoff is terrible. Now imagine a single dove in a population of hawks. He loses every contest, but he never gets hurt. His average payoff of 0 is actually better than the negative payoff hawks get from fighting each other. So dove genes would start spreading. The stable state turns out to be a mixture of hawks and doves. This ratio is stable not because it's good for the group. An all-dove population would actually do better collectively, but because it can't be exploited from within. A conspiracy of doves always leaves an opening for a selfish hawk to clean up. This simple model explains why animal aggression is often restrained. It's not nobility or concern for the species. It's what works best for the selfish individual in a world where everyone else is also playing to win. Now, back to that suicidal honeybee. This is genuine altruism, self-sacrifice. How can genes for this possibly survive? The answer lies in one of the book's most important concepts, kin selection. The key insight, developed by biologist W.D. Hamilton, is that your close relatives carry copies of your genes. You share about 50% of your genes with siblings, parents, or children, 25% with aunts, uncles, or grandparents, 12.5% with first cousins. From a gene's perspective, it doesn't just have one copy in your body, it has replicas in your relatives' bodies. So a gene for altruism can prosper if it causes you to save enough relatives to compensate for your own death. A gene for suicidal self-sacrifice would spread if it caused you to die, saving more than 2 full siblings. One copy is lost, but more copies are saved. Parental care is just a special case of kin altruism. A mother bird risks her life for her chicks because those chicks carry her genes. Genetically speaking, she should be equally willing to care for an orphaned baby brother as for her own son. The genetic relatedness is identical. But if this is true, why isn't family life always harmonious? This leads us to the battle of the generations. Think about it from a child's perspective. He's related to his mother by 1/2. He's also related to his brother by 1/2. So from a gene's perspective, he should want his mother to invest equally in his brother. But here's the catch. He's related to himself by 100%. He contains all his genes. From his selfish perspective, he's twice as valuable as his brother. This creates a natural conflict. A classic example is weaning. The mother wants to stop nursing so she can have another baby. The child wants to keep nursing as long as possible. There's a window where the child is getting more than its fair share from the mother's viewpoint. But the cost to future siblings is still less than double the benefit to itself. During this window, there's genuine conflict. Children aren't passive recipients of care. They're active strategists in this family drama, using every psychological weapon available, exaggerating hunger, crying louder than siblings, to grab more than their fair share of resources. The conflict between mates, the battle of the sexes, is even more intense because partners aren't related at all. The only thing they share is a 50% genetic stake in their children. The fundamental difference between male and female starts with their sex cells. Female eggs are large, nutritious, and rare. Male sperm are tiny, mobile, and produced by the millions. This single difference explains almost everything else. A female can only have a limited number of children in her lifetime. A male can potentially father enormous numbers. From conception, the female has invested more, her large, expensive egg, than the male has. She's more committed, which makes her vulnerable to exploitation. Ideally, a male would mate with as many females as possible, leaving each to raise the children alone. A female wants a partner who'll stick around and help invest in their shared offspring. This creates two main female strategies. The first is the domestic bliss strategy. The female plays hard to get, forcing the male into a long, costly courtship. This weeds out casual suitors. By the time he's finally allowed to mate, he's invested so much in time, energy, maybe building a nest or bringing food, that abandonment no longer pays. The second is the He-Man strategy. Here, the female accepts she'll get no help and focuses entirely on getting the best possible genes. She becomes extremely choosy, mating only with males who display the best evidence of being high-quality survivors. This creates a situation where a few lucky males win most matings. This explains features like the peacock's magnificent tail. A female mating with an attractive male will likely have attractive sons, giving her lots of grandchildren. The preference for attractiveness becomes a runaway evolutionary process. We've seen how cooperation can evolve between relatives. But what about strangers? This brings us to reciprocal altruism, or you scratch my back, I'll scratch yours. Imagine birds picking ticks off each other's heads, places they can't reach themselves. This makes sense. But what stops a bird from cheating, accepting grooming but refusing to return the favor? This is the classic prisoner's dilemma from game theory. In a one-time game, the only rational move is to cheat. But what if the same players meet repeatedly? This is the iterated prisoner's dilemma, and it changes everything. It allows for trust, forgiveness, and punishment. Political scientist Robert Axelrod ran a computer tournament to find the best strategy. The winner was remarkably simple, tit for tat. It starts by cooperating, then simply copies the opponent's previous move. Why was it so successful? It's nice. Never the first to cheat. It's retaliatory. Immediately punishes betrayal. It's forgiving, willing to cooperate again after just one punishment. And it's not envious. Happy for both players to do well together. This shows that even in a world of selfish genes, cooperation can emerge and thrive, as long as players know they'll meet again. The shadow of the future must be long enough. This explains cooperation in countless natural relationships, from cleaner fish and their clients to vampire bats sharing blood. We've journeyed from life's dawn through genes, survival machines, and complex social lives. But what about us? What about human beings? Dawkins argues that humanity's most distinctive feature can be summed up in one word: culture. Just as genes propagate by jumping from body to body, cultural ideas propagate by jumping from brain to brain. Dawkins coined a name for this new replicator: the meme. Examples include tunes, ideas, catchphrases, fashions, and technologies. They spread through imitation. And like genes, memes compete for survival, for our attention, for brain space, for room in libraries and on screens. The idea of God, for instance, is an ancient, successful meme. It has high survival value because of its deep psychological appeal. It became linked with other memes, like faith and the threat of hellfire, which reinforce each other and help the whole meme complex survive. Sometimes genes and memes oppose each other. A gene for celibacy would fail miserably, but a meme for celibacy, as part of a powerful religious complex, can thrive. Once our genes gave us brains capable of rapid imitation, memes took over and started their own, much faster form of evolution. This brings us to the final, most profound idea: the extended phenotype. Dawkins asks us to see that a gene's effects aren't confined to the body containing it. Genes reach out and manipulate the world. A beaver dam is a phenotypic effect of beaver genes. A caddisfly larva's stone house is an extended phenotype of its genes. But it goes further. Parasite genes can affect host bodies. A fluke can make its snail host grow a thicker shell, protecting both snail and fluke, but at the cost of the snail's reproduction. A cuckoo chick's genes manipulate the foster parent's brain like an irresistible drug, forcing it to feed the giant imposter. The central theorem of the extended phenotype: an animal's behavior tends to maximize the survival of the genes for that behavior, whether or not those genes are in the body of the animal performing it. Ultimately, the real distinction isn't between individual bodies but between replicators and their vehicles. Genes are replicators. Bodies are the vehicles they build to navigate the world. We've come full circle. We started with a simple question: why does life exist? The answer is that we, and all living things, are survival machines built by replicators. For billions of years, those replicators have been genes, DNA molecules. They built us, body and mind, and their preservation is the ultimate reason for our existence. But here, at journey's end, comes the most hopeful message of all. We're built as gene machines and cultured as meme machines. But we're the only creatures on this planet with the conscious foresight to understand what's happening. We can simulate the future and see the consequences of our actions. And because of that, we can turn against our creators. We alone on Earth can rebel against the tyranny of the selfish replicators. When you first encounter these ideas, they can feel a bit chilling. The notion that we're just robot vehicles blindly serving our genes seems to strip away our humanity, our free will, our sense of self. It paints nature as cold, calculating, and ruthlessly competitive. And in many ways, it is. Dawkins's great contribution was examining evolution with unflinching honesty. He didn't romanticize it or assign it higher moral purpose. He simply followed Darwinism's logic to its inevitable conclusion. In a world of replication, competition, and mutation, the only things that persist are the things good at persisting, and those things are selfish genes. But here's what I find powerful about this book. This seemingly bleak worldview actually opens a door to something profound. By understanding the deep underlying selfishness of our biological nature, we're finally in a position to do something about it. Think about the implications of the final chapters. Culture and memes created a second layer of evolution, operating far faster than the slow grind of genetic change. And consciousness. Our ability to reason, simulate, and have foresight gives us tools to consciously choose our path. We can see long-term cooperation benefits, where our genes only see short-term advantage. We can understand the prisoner's dilemma and choose to build systems of trust. We can care for the vulnerable even without genetic payoff. This book isn't a moral instruction manual. It doesn't tell us how we ought to behave. It tells us what we are at our biological core. It's a warning. As Dawkins writes, if you want to build a society where individuals cooperate generously toward a common good, expect little help from biological nature. We must teach generosity and altruism because we're born selfish. For me, that's incredibly empowering. It says our humanity isn't given to us. It's something we must build. It's a project, a choice. Our genes dealt us a certain hand, but we play the cards. We can rise above base-level programming. We can build a world where nice guys truly finish first, not just in computer simulations, but in daily life. We can use our big brains to pursue long-term interests, defying the short-term selfishness of the blind replicators that created us. That's the story of The Selfish Gene by Richard Dawkins. We've covered the main ideas today, but I'll be honest, a summary is like looking at a map of a beautiful country. It shows the layout and key landmarks, but can never capture the feeling of actually walking the paths, breathing the air, discovering hidden treasures yourself. The real magic happens when you read the book. It's in those quiet moments when a particular story or simple phrase hits you unexpectedly. This summary gives you a taste, helps you decide if this journey is one you want to take. If anything we've discussed has sparked your curiosity, grab a copy. Reading it isn't just about learning. It's an experience that can genuinely change how you see yourself and your place in life's grand story. If you found this summary valuable, I'd be grateful if you'd hit the like button and subscribe to the channel. It lets me know these journeys are meaningful to you and ensures you won't miss our next exploration into another life-changing book. Let's keep growing together.